Of all the objects in the cosmos,
Planets,
Stars.
galaxies.
none are as strange, mysterious, or powerful as black holes.
Black holes are the most mind-blowing things in the universe.
They could swallow a star completely intact.
Black holes have these powerful jets that just spew matter out.
First discovered on paper,
On the back of an envelope, some squiggles of the pen.
the bizarre solution to a seemingly unsolvable equation,
A mathematical enigma.
Einstein himself could not accept black holes as real.
People didn't even believe for many years that they existed.
Nature doesn't work that way.
Yet slowly, as scientists investigate black holes,
by observing the effect they have on their surroundings.
evidence begins to mount
That is the proof of a black hole.
Millions of times the mass of the sun.
cutting-edge discoveries show
We did it.
black holes are very real.
I thought it was crazy.
I said, holy.
But what exactly are they? If we could visit one, what might we see? With their immense power, do black holes somehow shape the very structure of the universe? Is it possible we might not exist without them?
It's quite a journey.
Black Hole Apocalypse, right now on Nova. There are apocalyptic objects in the universe, engines of destruction, menacing and mysterious. Black holes. Even scientists who study them find them astonishing.
Black holes can sort of blow your mind. I'm amazed that these objects actually exist.
Black holes defy our understanding of nature.
Black holes are the greatest mystery in the universe.
They're completely invisible, yet powerful beyond imagining. They can tear a star to shreds.
Black holes actually will eat anything that comes in their path.
You really want to avoid them at all cost.
Black holes even slow time. Once thought too strange to be real, black holes shatter our very understanding of physics. But we're learning they may somehow be necessary for the universe we know to exist.
They might well be the key players in the universe.
What are these strange, powerful objects? Outrageous and surprising. Where are they, and how do they control the universe? The search for black holes is on, and it will be a wild ride across the cosmos to places where everything you think you know is challenged, where space and time, even reality, are stranger than fiction. And we're starting that journey at a very unlikely place. Here, at a remote location in Washington State, where for the first time, a radical new experiment has detected black holes. It originated over 50 years ago, when a few visionary scientists imagined a technology that hasn't yet been invented. Searching for something no one is certain can be found. The experiment is daring and risky. Failure could mark their lives forever. But they don't fail. Right here in these facilities, they make a remarkable discovery. In the early hours of September 14th, 2015, they record a message. It looks and sounds like this. Just a little chirp. But that chirp is epic, monumental. The signal traveled over 1 billion light years to reach us. It started far, far away. And what it tells us is this. Somewhere in the cosmos, over 1 billion years ago, 2 massive black holes circle each other in a fatal encounter. Closer and closer they come, swirling faster and faster, until finally they slam together. The black holes create waves that spread outward, just like vibrations on a drum. A ringing in the fabric of space itself. The collision creates a massive blast, putting out 50 times as much power as the entire visible universe. It sends out a wave not of heat or light or sound, but of gravity.
This gravity wave is moving its way through the universe at the speed of light.
The wave races by stars. On the young Earth, supercontinents are forming. Microscopic organisms have just appeared.
Washing over one galaxy after another, after another.
Dinosaurs roam the Earth.
The wave is still moving.
It zooms through clouds of dust.
And then it nears the Milky Way galaxy.
The Ice Age is just beginning.
We're troglodytes, drawing in caves.
The wave reaches nearby stars. Albert Einstein is in the 6th grade. The wave approaches as close as Alpha Centauri. At midnight on September 13th, 2015, it is as close as Saturn. Finally, over 1 billion years after the black holes collide, the wave reaches us. It strikes a pair of revolutionary new observatories, the sites of the daring experiment. This is LIGO, the Laser Interferometer Gravitational Wave Observatory. The experiment, 50 years in the making, has finally hit the jackpot and opened an entirely new way of exploring the universe. For 400 years, almost everything we've observed in space has come to us in some form of electromagnetic energy. That little chirp is different. What hits the Earth in September 2015 is a gravitational wave, a squeezing and stretching of the very fabric of space. It produced no light. No telescope could ever see the collision. We needed an entirely new kind of observatory to detect it. That wave is new and direct evidence of one of the strangest mysteries in our universe, black holes. Most of us have heard of black holes. They're invisible, powerful,
We're talking about things that are 1 billion times the mass of the sun.
Bizarre. A physical entity with infinite density. No beginning, no end.
They pull things in and warp light. Approach one, and time itself begins to change.
The gravity is so intense that a moving clock will tick slower.
Time will become so slow for you that you will watch the entire future of the universe unfold before your very eyes.
Fall in, and you'd be squeezed as thin as a noodle.
You'll be extruded through the fabric of space and time, like toothpaste through a tube.
Today, we know more about black holes than ever before. But the more we learn, the more mysterious they become.
They're the most exotic objects in the universe. We don't have the physics to describe them.
No matter how well you understand them, they remain unreachable in some sense.
Now, gravity's at maximum. Man is about to enter the black hole.
So black holes have a pretty fierce reputation. And if you want a villain for a sci-fi movie, cast a black hole. But in reality, what exactly is a black hole? And where do they come from? You might think a black hole is like this, an object, but it's not. It's a hole in the fabric of space, a place where there is nothing except gravity, gravity at its most intense and overwhelming.
So if black holes are all about gravity, gravity at its most extreme, what exactly is gravity?
We're all familiar with gravity.
Yep, it's Friday.
It rules our lives. But even so, for a very long time, how gravity actually works was one of the greatest mysteries. Over 300 years ago, Isaac Newton was fascinated with the behavior of moving objects. Eventually, he figured out his laws of motion. They work so well, we still use them today.
We have liftoff at 9:34 a.m.
But Newton's laws can only describe gravity's effects, not explain what it is. And here's where Albert Einstein comes in. Like Newton, he thinks about objects in motion. And he wonders what gravity actually is. Is it a force, or could it be something else? Here's what concerns Einstein. Take this apple. I can't move it without touching it. But if I drop the apple, it moves toward the earth. But what if I take my hand away, and the floor, and the basement, and the floor below that? Then what happens? The apple just keeps falling. Einstein realized that gravity had something to do with falling. Now, if I throw the apple, it falls along a curved path. But imagine I could get the apple moving much faster. Eventually, if I get the apple moving really, really fast, say 17,000 miles an hour, its curved path matches the curve of the Earth. The apple is in orbit, falling freely, just like the International Space Station and the astronauts inside it. According to Einstein, the apple and the space station and the astronauts are all falling freely along a curved path in space. And what makes that path curved? The mass of the Earth.
Einstein came up with a supremely simple concept, and that is that space and time is bent by the Earth and by the sun and by all the objects in the world.
So according to Einstein, the mass of every object causes the space around it to curve.
And that was Einstein's conception. There are no forces anymore. There's just objects bending space-time and other objects following the straightest line through it.
All objects in motion follow the curves in space. So how does the Earth move the apple without touching it? The Earth curves space, and the apple falls freely along those curves. That, according to Einstein's general theory of relativity, is gravity, curved space. And that understanding of gravity, that an object causes the space around it to curve, leads directly to black holes. But it's not Albert Einstein who first makes the connection between gravity and black holes. It's another scientist.
Karl Schwarzschild was a German astronomer head of the Potsdam Observatory in Germany.
Ever since he was a teenager, he had been calculating complicated features of planetary orbits.
As Einstein unveils his theory of gravity in 1915, Karl Schwarzschild is in the German army, calculating artillery trajectories in World War I.
And just weeks after Einstein presented his papers, Schwarzschild, then on the Russian front, quickly got a copy and was mapping the gravitational field around a star.
Einstein had gotten at it through a series of approximations, but Schwarzschild, sitting on the front with bullets and bombs flying, calculated an exact solution to Einstein's theory and sent it to Einstein. Einstein was astonished. He hadn't even imagined that you could solve these equations exactly.
But Schwarzschild isn't done. In his solution to Einstein's equations, he discovers something Einstein himself had not anticipated.
Schwarzschild said, I can calculate this strange distance from a gravitating object that represents a kind of a boundary.
Schwarzschild mathematically concentrates a mass, for example, a star, into a single point. Then he calculates how that mass would bend space and curve rays of light passing nearby.
As he, through his mathematics, aimed particles of light or matter towards this point, there was this boundary surrounding the point at which the particles would just stop. The particles disappeared. Time stopped.
Schwarzschild has discovered that a concentration of mass will warp space to such an extreme that it creates a region of no return. Anything that enters that region will be trapped, unable to escape, even light.
It's like those roach motels. You can check in, but you can't check out. Once you go across that boundary, even if you can sail through, there's nothing you can do to get out. There's nothing you can do to signal out. It becomes this strange cut-off portion of space-time.
What Karl Schwarzschild has discovered is that any mass compressed into a small enough space creates what we today call a black hole. But Albert Einstein, whose own theory of gravity predicts such a thing, cannot believe it can happen in the real world.
Einstein didn't think that nature would act like this.
He didn't like this idea.
Karl Schwarzschild becomes ill and dies before he has a chance to further investigate his own discovery. 2.5 years later, in November 1918, World War I ends. The strange theoretical sphere discovered by Karl Schwarzschild seems destined to be forgotten. Nothing but a curious historical footnote. But in the coming decades, physicists learn more about the atom and about how fusing atoms powers stars, a process called nuclear fusion. Some begin to wonder if something like a black hole could actually come from a star. But not just any star. It would have to be big.
Stars are born in litters, and you get a distribution of sizes and masses. Thousands of little stars, and a few big stars, very big stars, incredibly massive.
Stars are in many ways similar to living creatures. Like humans, they have life cycles.
Investigating stars' life cycles in the 1930s, two visionaries, Subramanian Chandrasekhar and Robert Oppenheimer, discover that the most massive stars end their lives very differently from smaller ones.
The life cycle of a star really depends on its mass. The mass of a star determines what's going to happen after it finishes burning its hydrogen fuel.
All stars start out burning hydrogen, the lightest atom, fusing hydrogen atoms into helium, working their way up to heavier elements. Gravity wants to crush the entire mass of the star, but the enormous energy released by fusion pushes outward, preventing the star from collapsing.
Stars are stable because we have an outward moving pressure due to nuclear fusion, and that's balancing with the inward force of gravity.
Smaller stars can't fuse elements heavier than helium. But in the most massive stars, fusion crushes heavier and heavier atoms, all the way up to iron.
Iron is such a massive element, it has so many protons in it, that by the time you fuse iron, you don't get any energy back out.
Iron is a dead end for stars. Fusing atoms larger than iron doesn't release enough energy to support the star. And without enough energy from fusion keeping the star inflated, there's nothing to fight gravity.
And gravity wins. And so the entire star collapses.
Very rapidly, trillions of tons of material come crashing down, hit the dense core, and bounce back out, blowing off the outer layers of the star in a massive explosion. A supernova. The more mass, the more gravity. So if the remaining core is massive enough, gravity becomes unstoppable.
There's no known force to prevent the collapse to an infinitesimally small dot.
Gravity crushes the stellar core down smaller and smaller and smaller until all its mass is compressed in an infinitely small point. A black hole. The theory makes sense, but most physicists remain skeptical about black holes.
Einstein and Eddington, all the sort of, preeminent astrophysicists in the 1930s through 1950s did not believe that they were actually real. It remained a solution, a mathematical enigma for a very long time. So it took a long time for people to even start looking for them.
It's not until the 1960s that the idea of a supernova creating a black hole is taken seriously. Princeton physicist John Wheeler, who had originally been a skeptic, begins to use a name from history for these invisible objects: black hole.
The term black hole actually originates in India. The black hole was the name of an infamous prison in Calcutta.
Still, no one has ever detected any sign of a black hole. Then in 1967, graduate student Jocelyn Bell discovers a strange, extremely tiny, dead star that gives off very little light. A neutron star. The cold remains of a stellar collapse. The neutron star gives astronomers more confidence that black holes, much heavier dead stars, might also exist. A half-century after Carl Schwarzschild mathematically showed that black holes are theoretically possible, scientists have identified a natural process that might create them: the death of large stars.
So these giant supernova explosions of extremely massive stars make black holes.
Any star that is born with a mass that's about 10 times the mass of the sun or higher will end in a black hole. So our galaxy is replete with little black holes, which are the stellar corpses of generations of stars that have come and gone.
So what are these invisible stellar corpses like? Imagine I'm exploring space with some advanced technology for interstellar travel so that we could visit a black hole, maybe one in our own galactic neighborhood. This particular black hole isn't very big, only about 10 solar masses, meaning 10 times the mass of the sun. And like all black holes, it has an event horizon, a distinct edge to the darkness. That's the boundary Carl Schwarzschild first discovered, where gravity is so strong that nothing can escape, not even light. And that's where we're going. As we get closer, some very strange things begin to happen. Look at the edge of the black hole. See how the image of distant stars is distorted and smeared into a circle? That's gravitational lensing. The black hole's extreme gravity bends the path of light passing by, so that a single point of light, like a star, briefly appears as a ring around the event horizon. I'm now deep in the black hole's gravity well, and we're going to start experiencing the effects. The extreme gravity actually slows down time relative to the Earth. From their point of view, I appear to be slowing down. But from my point of view, time on Earth is speeding up. Now let's say I want to get even closer by taking a spacewalk. The way the black hole slows down time is about to get even more pronounced. To keep track of the changes I'm about to experience, I'm turning on this strobe light. It'll blink once a second. From here, I can see the shadow of the event horizon approaching, and my light blinking normally. But watching from the ship, the closer I move toward the black hole, the more slowly I appear to move. The pulses are nearly infinitely spaced. So it looks as though I'm frozen in time. For me, everything is completely normal, even when I reach the event horizon. If you waited long enough, maybe millions or billions of years, the ship would finally see me disappear. And that's the last you'd see of me. What's inside a black hole? That's still a mystery. And even if I find out, I can never go back and tell you. But I can say this. Black holes may be dark from the outside, but inside they can be bright. I can watch the light from the galaxy that's fallen in behind me, and that's the last thing I'll ever see. Unfortunately, the fun is about to end. Now that I've crossed the event horizon, I'm falling toward the center, where all of the mass of the black hole is concentrated. And I'm beginning to get stretched. As I fall in, the gravitational pull at my feet is stronger than at my head, and my body is starting to get pulled apart. I'll be stretched as long and thin as a noodle, spaghettified. And ultimately, I'll end up completely disintegrating into my fundamental particles, which are then crushed to an infinitely small point. A singularity, where everything we understand about space and time breaks down. Or maybe the black hole, less than 40 miles across on the outside, is as big as a universe on the inside. And as I pass through, my particles will join the primordial soup of a new beginning. So that's what theory tells us we might experience if we could travel to a black hole.
can we know for sure? How do you investigate something you can't even see? There are ways to investigate if something is happening somewhere, even if I can't see that thing directly. Take Yankee Stadium. What's happening inside there? Is there a game going on? I can't see the field. I can't see any players or baseballs or bats, but I can definitely tell if there's activity around the park. It's pretty clear something is going on. It might seem obvious, but whatever it is, I can learn a lot just by observing the happenings around the stadium. And these do look a lot like baseball fans. And that's the way we investigate black holes, by observing the effect they have on their surroundings. But what sort of effects? How might a black hole reveal itself? Starting just before World War II, two monumental discoveries are about to radically change astronomy. In 1931, Bell Labs engineer Carl Jansky picks up mysterious radio waves emanating from deep space. Then the sky gets even stranger. When scientists mount Geiger counters on captured German rockets and discover the cosmos is also full of X-rays. These discoveries give astronomers important new tools that will revolutionize the hunt for black holes and dramatically expand our vision.
What our eyes can perceive is a very narrow part of the electromagnetic spectrum.
If the electromagnetic spectrum were laid out along the Brooklyn Bridge, the portion we can see with our eyes would be just a few feet wide. Electromagnetic radiation includes waves of many different frequencies: radio waves, microwaves, infrared and ultraviolet light, X-rays, and gamma rays. Radio and X-ray astronomy open up the sky, revealing dim or even invisible objects, blasting out powerful energy no one knew was there.
They began to realize that this very placid thing that we see out there, all this very quiet thing that looks like nothing is happening and the only thing that's moving is the planets, found out that there was madness going out there. There was chaos out there.
X-rays come from the high energy end of the spectrum. What is creating all this energy? This much is certain. Whatever the source, it is invisible to ordinary telescopes, and it is hot.
X-rays come from things which are at temperatures of millions of degrees, even tens of millions.
One of the first of these X-ray sources to catch the attention of astronomers is named Cygnus X1.
Cygnus, it was in the constellation Cygnus. X, it was an X-ray source. 1, it was the first one you found.
In 1970, Paul Murden is a young English astronomer trying to secure his next job.
I was a research fellow. I was coming to the end of my 3-year contract, and I thought, what can I contribute to finding out what these things are?
Murden works in a 15th century castle surrounded by telescopes, the Royal Observatory. Using the largest telescope in England, he begins searching the area of the constellation Cygnus, the Swan. He decides to hunt for pairs of stars. Pairs of stars are called binaries. They may sound exotic, but they're not at all uncommon. Many of the stars we see, perhaps half, are actually binaries, pairs of orbiting stars locked together by gravity. But Murden wonders, is it possible there are binaries where only one of the stars is visible?
I thought that maybe there was a kind of a star system in which there was a star, one ordinary star that made light, and then there was another star nearby that made X-rays.
The telltale sign of a binary is that the stars are moving around each other. So Murden begins searching for a visible star that shows signs of motion.
Sometimes it's coming towards you, sometimes it's coming away. Sometimes it's coming towards you, sometimes it's coming away.
When the star is moving toward us, it appears more blue as the wavelength of its light gets shorter. Moving away, it appears more red as the wavelength of its light gets longer. This is known as Doppler shift. After looking for color changes in hundreds of stars in the area of Cygnus, Murden spots a possible suspect, a visible star whose light is shifting as though moving around.
It very clearly was a binary star, a double star. The star was moving around and around with a period going round once every 5.6 days.
But whatever it's going around can't be seen.
There was no trace in the spectrum of the second star. There was one star there, there wasn't the second star there.
Murden has a binary pair in which only one star is visible. The second object emits X-rays, has enough mass and gravity to dramatically move a star, but gives off no light. Could it be the corpse of a star massive enough to become a black hole?
The crucial issue in deciding whether Cygnus X1 was a black hole was to measure the mass of the X-ray emitting object.
It would have to be very massive, at least 3 times the mass of our sun. If not, it's probably just a neutron star. A collapsed star that's dense, but not heavy enough to be a black hole.
So the observers needed to come up with a conclusion that the dark object, the X-ray emitting object in Cygnus X1, was heavier, hopefully substantially heavier than 3 solar masses.
From his observations, Murden is able to make an estimate of the mass of the invisible partner.
And the answer came out to be 6 times the mass of the sun. So there was a story then that Cygnus X1 was a black hole. And the key to the argument was that the mass of the star you couldn't see was more than 3 solar masses. When I'd finished writing it all out, I sat back and thought, it's a black hole.
This would be the first actual detection of a black hole. It's a huge claim, and Murden will have to convince skeptics, starting with his boss.
The Astronomer Royal, Sir Richard Woolley, he didn't really go for black holes. It's all fanciful. It's a lot of people in California were talking about this. There are a lot of funny people in California, you know, a lot of hippie-type people.
People like theorist Kip Thorne.
So I was nervous about it. I was nervous about the scale of the discovery, and actually so were other people all around me. I was working with a fellow scientist, Louise Webster, and we were modest about the claim that we were making because we knew what people would think of it. And if you look at the paper we published, it just mentions the word black hole once, right at the end. We think this might be a black hole.
The Paul Murden Louise Webster paper appears in September 1971. Other astronomers agree it could be a black hole, but no one knows for sure. 3 years later, Kip Thorne and the noted British physicist Stephen Hawking make a now famous wager about Cygnus X1.
We made a bet as to whether Cygnus X1 really was a black hole or not.
The bet is partly in jest. Both men hope it is a black hole. But Hawking, not wanting to jinx it, bets against his own wishes.
Stephen claims that Cygnus X1 is not a black hole, and I claim it is a black hole. And so we signed that bet in December 1974. And gradually, the case that it really was a black hole became stronger and stronger and stronger. So in June of 1990, Stephen broke into my office, and he thumbprinted off on this bet, conceded the bet in my absence. I came back from Russia and discovered that he had conceded.
Now, by 1990, the evidence of Cygnus X1's mass may be strong enough to settle a bet between two friends. But the original estimate wasn't precise enough to be definitive. In order to calculate mass, Paul Murden had to rely on rough estimates of the distance to Cygnus X1, which varied by a factor of 10. And the question wouldn't be answered for another 20 years, until astronomer Mark Reed became intrigued by the puzzle. Reed is an astronomer at the Harvard-Smithsonian Center for Astrophysics when he sets out to conclusively prove that Cygnus X1 is a black hole by measuring its precise mass. But how can you measure the mass of an invisible object? Using laws developed by German astronomer Johannes Kepler in the 1600s, it's possible to calculate the mass of a celestial object, but only if you know its distance.
Distance in astronomy is absolutely fundamental. If you don't know distance, you don't know what the object is. Could be a very nearby firefly-like thing. It could be a very distant, huge star, much, much bigger than the sun.
So to get the true, precise mass of Cygnus X1 and confirm that it is a black hole, Reed needs to know how far away it is. But how can he measure the distance to a star? The secret lies in a familiar phenomenon, parallax. It's what our eyes and brains use to see in 3 dimensions.
You can put your finger up at arm's length, look at it, and close one eye. I'm closing my left eye, and I'm looking at my finger relative to the wall in the background there. And now if I open my eye and close my right eye, I see my finger has appeared to move with respect to the original position. And that's because our eyes are separated and we view from different vantage points.
To use parallax to measure distance to an object in the sky, astronomers let the motion of the Earth provide the 2 different vantage points.
Imagine Cygnus X1 is right here, and the Earth and the Sun are over there. Now, the Earth goes around the Sun once a year. And in the springtime, the Earth ends up on one side of the Sun, and we observe Cygnus X1 along a ray path like this. And 6 months later, the Earth goes around the Sun to the other side. We get a different vantage point from Cygnus X1.
Now he has a triangle that goes between the Earth at its 2 positions and Cygnus X1. We know the base of the triangle, the diameter of Earth's orbit. And the principles of geometry tell us that all we need to calculate the distance is the size of the angle at the top.
And we measure this very small angle here at the point at Cygnus X1. And then from direct geometry, we can calculate the distance to Cygnus X1, and from that infer a very accurate mass.
The concept is simple, but Cygnus X1 is so far away that the angle to be measured is minuscule, a tiny fraction of 1 degree. It's smaller than the angle spanned by Abraham Lincoln's nose on a penny in San Francisco, viewed from New York. Because the angle is so very tiny, it can't be measured by any one telescope. But Reed's team has a solution.
We take 10 radio telescopes that are spread across the continental US and to Hawaii and to St. Croix in the Virgin Islands. We use these telescopes simultaneously, and we synthesize in the computer a telescope that has the diameter of the size of the Earth. That gives you incredible angular resolution.
Using this technique, Reed's team determines that Cygnus X1 is 6,000 light years away.
With the new distance we got, the 6,000 light-year distance, we were able to determine that the mass is about 15 solar masses, easily a black hole.
40 years after it was identified as a possibility, Cygnus X1 is now widely accepted as the first confirmed black hole.
It's an understated paper, and the fact that my name was on it and Louise Webster's was on it did us a lot of good in our careers. I think as a result of this discovery, I got offered a permanent job, and it was a great celebration for the family. So it worked out very well for me, as well as getting the intellectual satisfaction of solving a problem.
So finally, after years of speculation, we have a real black hole. Not only that, but a black hole that's blasting out X-rays and has a companion star. If we could visit in my imaginary spaceship, what would we see? The distance to Cygnus X1 has been established at 6,000 light years from Earth. And its mass is 15 solar masses, or 15 times the mass of the Sun. And Cygnus X1 is surrounded by an accretion disk, a disk-shaped cloud of gas and dust outside its event horizon, the point of no return. As gravity pulls matter toward the black hole, the cloud starts rotating, just like water being pulled down a drain. Within that accretion disk, particles closest to the black hole whip around at half the speed of light. It's like a giant particle accelerator in space. But why does it emit X-rays? As those particles race around, they collide, which heats them up to millions of degrees. When they get that hot, particles blast out X-rays. And it's those X-rays that first led astronomer Paul Merton to investigate this black hole nearly 5 decades ago. And there's something else about Cygnus that's different. It has a companion star. This blue supergiant star orbits the black hole once every 5.6 days. It orbits so close to Cygnus X1 that the black hole strips material off the star and pulls it into the accretion disk. Some of that material will cross the event horizon and get swallowed up, but not all of it.
Some of the stuff actually comes back out before ever entering the black hole. Kind of like a toddler eating. Half the pasta ends up on the floor, half of it maybe on the ceiling, and some of it in the mouth.
One of the most striking and enigmatic features of Cygnus X1 is its enormous jets. These beams of particles and radiation stream outward from Cygnus's north and south poles, perpendicular to the accretion disk. There's still a lot we don't know about these jets, but they are tightly focused and extremely powerful, blasting out at nearly the speed of light and extending well beyond Cygnus.
When gas gets to these high temperatures and produces the light, there's also a little bit of a magnetic field that forms around them. And we don't understand exactly how, but these magnetic fields help collimate these massive outflows from black holes. Powerful hoses, if you will, that just spew matter out.
So that's Cygnus X1, if we could see it up close. A growing, feeding black hole with huge jets, blasting particles way out into the universe.
They're almost these breathing, fire-eating demons, if you will. They flicker, they have bursts. It's a very violent fireball, very active.
What was once a bizarre mathematical curiosity has now become quite real. After decades of skepticism, scientists now accept that burned out corpses of large stars can trap light inside them, warp space and time around them, attract matter, and accelerate it to mind-boggling speeds.
Black holes seem like such a radical idea that we shouldn't accept it. But bit by bit, the evidence for black holes has gotten stronger and stronger. And we've seen these amazing things.
At least 20 black holes have been found in our galaxy. X-ray binaries like Cygnus X1. And there are probably millions more of these massive stellar corpses in our galaxy alone. Still, a stunning surprise awaits. Everything astronomers think they know about black holes, and much of what they believe about the universe itself, will be upended by a shocking discovery. The revelations begin when radio telescope surveys of the sky detect mysterious hot spots emitting radio energy.
They were coming from what looked like stars.
Because these objects resemble stars, but were discovered through radio signals, astronomers name them quasi-stellar radio sources, quasars. But are they stars or not? The first step in investigating them is to figure out what they're made of. To do that, astronomers analyze the electromagnetic energy they emit. Every element has a unique spectral fingerprint. For example, carbon, helium, hydrogen. These lines reveal the chemical makeup of a star. But the spectrum of a quasar turns out to be incomprehensible.
They looked at it and it was gibberish. It didn't look like there were any emissions from elements that they knew.
What are they missing? There has to be a clue somewhere. Finally, in 1963, Caltech astronomer Martin Schmidt finds it, hiding in plain sight. Buried in the quasar spectrum is the fingerprint of hydrogen.
He noticed something familiar, but it was in the wrong place. The fingerprints of hydrogen had been shifted way off to the red.
It was hard to spot because the spectral lines of hydrogen were radically shifted toward the lower frequency end of the spectrum, and that could only mean one thing. The quasar is moving away from us at fantastic speed. But astronomers have never before seen light shifted to such an extreme. Like a familiar sound shifting too low to understand. The light from quasars has shifted to such a degree that hydrogen is unrecognizable. This extreme amount of shift means quasars are racing away from us at blinding speeds. The reason? It's the legacy of an event that occurred almost 14 billion years ago, the Big Bang. The beginning of our universe. And ever since, the universe has been expanding, carrying with it all the objects it contains, including quasars.
No one had ever seen anything moving away at that high speed. This made this object the furthest away thing that had ever been seen, which meant the thing itself had to be so luminous, and you had to account for that.
2 billion light years away, putting out the energy of 1 trillion suns each second. What could possibly create that?
No one had any idea what could be powering these things. Where could all of this energy come from?
If you work out through calculations, it can't be chemical energy. They knew it couldn't be nuclear energy.
There's no way a quasar could be a star. No amount of nuclear fusion could produce that much star power.
The only engine that could possibly put out that much energy is gravity.
Gravity. In everyday life, we can overcome gravity easily. But when concentrated to an extreme by a black hole, gravity is overwhelmingly powerful. A handful of scientists start wondering,
Could quasars perhaps be powered by gravity engines? What if the energy blasting out from quasars is coming from bright accretion disks around black holes?
To produce that kind of energy, that kind of brightness, it has to involve a black hole.
But not just any black hole.
Whatever was the source of the emission from a quasar had to be massive. How massive? Well, millions or billions of times heavier than the sun.
Millions or billions of times heavier than the sun. Cygnus X1 is only 15 times the mass of the sun. The black holes powering quasars are an entirely different category of black hole. Supermassives. And they seem to be located in the centers of galaxies. But what about our own galaxy? Could there be any supermassive black holes closer to home? The center, where any supermassive would be found, lies in the direction of the constellation Sagittarius, the Archer. Now, Sagittarius isn't just any constellation. It's in the direction of the center of our own Milky Way galaxy. But since we live inside the Milky Way, we can't see the galaxy the way a space traveler would. But I can use my trusted imaginary star machine to show us the galaxy from the outside. Our home is a spiral galaxy, hundreds of billions of stars drawn together into a gigantic disk. It's wide, about 100,000 light years across, but it's relatively thin, only about 1,000 light years thick. And the whole spiral slowly rotates. Our solar system is here. And here, 26,000 light years from the Earth, is the center, which we see in the direction of Sagittarius. In this dense center, there are millions of stars and lots of dust and gas. So that's the view of our galaxy from the outside, thanks to my imaginary technology. But since we live inside the Milky Way, when we look towards the center, we're looking through much of our own galaxy, which means it appears to us as a band of stars and dust across the sky, a Milky Way. Deep inside this band of stars and dust, could a supermassive black hole be lurking?
The data that we're getting now, where it is now.
In the 1990s, astronomers grow determined to solve the mystery, to peer through the murky Milky Way and learn what, if anything, is at its center. One of them is Andrea Ghez.
1 in 20.
Ghez takes on a daunting challenge. She will try to track individual stars orbiting the center of the galaxy.
The essence of this experiment comes from watching stars orbit the center of the galaxy. So you want to find the stars that are as close to the center of the galaxy as possible, which means that I want to get access to the largest telescope I can possibly get my hands on.
And that means coming here. The summit of Mauna Kea, a dormant volcano almost 14,000 feet above the beaches of Hawaii. High altitude and low humidity make this the ideal place for astronomy. The instrument Ghez uses is Mauna Kea's Keck Observatory, one of the largest in the world. But despite its size, Keck has the same problem as all telescopes on Earth: atmospheric distortion.
Think about looking at a pebble at the bottom of a river. The river is moving very quickly, and your view of that pebble is distorted.
Like a river, the Earth's atmosphere is constantly changing, bending light like a funhouse mirror. To compensate for this, Keck pioneers the scientific use of a declassified military technology called adaptive optics. First, They shine a laser into the sky, creating an artificial guide star. The turbulent atmosphere distorts the guide star. But the computer knows what it should look like and adjusts the telescope mirror accordingly.